In this video, we'll discuss non-standard linear programming problems, and we'll use the simplex method just like before to solve them. A non-standard problem is a problem that has mixed constraints. So if you recall from before, when we talked about a standard linear programming problem, we were either maximizing or minimizing some kind of objective function, and we had only one kind of constraint, depending on whether it was maximizing or minimizing. In other words, the constraints were either less than or equal to or greater than or equal to. It was one of these two kinds of constraints. That was it. Okay? In the non-standard problem, we include all kinds of constraints altogether. The problem here is that we can't use our dual method that we used before. Okay, so if we have a minimization problem or a maximization problem, we have other methods to solve these kinds of problems. But in fact, it's pretty straightforward. In other words, it's very similar to what we've talked about before for the standard problem. The only difference is we have to include other kinds of variables, like slack variables, to make all of these things equalities. And in fact, even though this is an equality, we still have to add an additional variable to this thing because we want to differentiate an equality constraint from the actual objective function. So again, a non-standard problem is a problem of linear programming where we're trying to maximize or minimize some kind of objective function, just like before. The only difference is we have mixed constraints. They could be any one of these kinds or all of them together. Okay? And of course, in an actual problem, the coefficients are not all the same, and these b's are not all the same, as we'll see. It's just I wrote these down to show you all of the kinds of constraints that we could have in a non-standard problem, one given problem. Okay, so let's talk more about how we might set up a problem like this with mixed constraints. So now I've written down the different kinds of constraints that we could have in a non-standard problem. Again, in general, they're mixed, and we could have all of these or some combination of them. So for each case, we have to be a little bit more careful, and we want to turn all of the inequalities into equalities. And of course, even if we have an equality constraint, we have to differentiate the equality constraint from the actual objective function. So just like we worked with the standard problem, we want to introduce these other variables. Okay, these variables like the slack variable, right, to make them an equality. So it turns out that for the less than or equal to, it's just like usual. This, again, is going to be a slack variable. So in other words, I add S1 here, S indicating slack, to make this an equal sign, right? If I add something to something that's less than something else, it could become equal to. So add the slack to make up the slack so it's actually an equal sign here. Okay? So that's what I do. That's the slack variable. So for this first kind, this is slack. Okay? So if it's a less than or equal to, it becomes an equal when I add the slack variable. For anything that has a bigger than or equal to sign, I have to, well, this thing's bigger than b, right? So I have to subtract something. This is called a surplus variable. So I subtract S2 maybe, just to keep track of the s's, S for surplus and slack, but this is a surplus variable. Okay? You can read my writing. Okay, so there's a surplus variable. And I subtract that from this quantity that's bigger, and then it becomes an equal sign. So I get an equal sign here, okay, when I do that. Again, that's the goal, is to turn all of the inequalities into equalities. It's just that when I have a mixed set of constraints, I cannot use the dual problem that we talked about before. We have to introduce another variable called the surplus variable. Okay, so the slack variable and the surplus variable, S1 and S2. And similarly, down here when I have an equality constraint, again, I have to differentiate this from the actual objective function. So I include something else. This is called, unfortunately, I'm going to label it with an A, just like these, but you know, in general, you'll be able to put an A there, and you'll have numbers here for the red A's over here. But this thing, we'll call it A1, okay? And this is called an artificial variable. Okay? And the artificial variable is something that makes this constraint something that I can work with, and it makes it different than the actual objective function. That's the idea, okay? So if I have an equality constraint, I need to add this extra artificial variable. Don't forget, if it's a constraint. Notice again, all of these extra variables I'm adding are only added to the actual constraints, okay? So if I add a slack variable, a surplus variable, or an artificial variable, now I can go ahead and take my corresponding problem and put it into a tableau, which is of course a matrix, and go ahead and do the usual process. Okay, we go from corner point to corner point until we find the optimal corner point. For a non-standard problem, it turns out that the work that we have to do is a little bit more complicated because there's more things to keep track of. But for the most part, the operations are very similar to the standard problem. Okay? The only difference, again, has to do with the constraints. We have a set of mixed constraints. So we have to introduce some more of these, in some sense, artificial things to the overall problem. That is a slack variable, a surplus variable, and an artificial variable indicated by S's and A's. Okay? The only difference between a slack variable and a surplus variable is that one you add and one you subtract. Okay? So that's the general idea. One more word of caution when working with non-standard problems. Specifically, non-standard problems that have an equality constraint, so that we have artificial variables. Now, we include artificial variables because we have to work with this as a constraint, but we also must be careful not to come up with this as a solution to our problem, because it's something that we've added, it's artificial, meaning that the constraint holds without this at all. Now, it's possible to have a solution for a slack variable, as we've seen, but it's not possible to have one for an artificial variable because it's artificially added to the problem. So here's my caution word of warning. Okay, a curvy road is coming soon. The artificial variable cannot be a basic variable. That's the point, because if it were, it would be a solution. So the point is that if the artificial variable cannot be made zero, the problem has no feasible solution. So made zero meaning that it has to be made a non-basic variable. You can't have it be a basic variable. If it does, the problem doesn't have a solution because we've artificially added something to the problem. Okay? And of course, that's different than a slack variable. But for an artificial variable and working with mixed constraints, we have to be more careful with the equality constraint in particular. And we'll see some examples with this kind of problem where we have mixed constraints including an equality constraint. And we'll see how this works.